So before our big reveal of conservation of energy and how to solve conservation of energy problems, we have to look at two different types of forces, okay? These make a difference when we're talking about conservation of energy. And these two types of forces are called non-conservative forces and conservative forces, okay? And here's how they're different. Non-conservative forces, and if you could go to that slide that says non-conservative forces. Non-conservative forces, the change in energy of the object moving through that force, okay, or acted upon by that force, is dependent on the path, okay? So what does that mean? So let's say that I want to get an object here from A over here to B, okay? As you know, there are many, many different paths I can take. I could go from here to here. I could go from here all the way up here and then over to here, right? Or I could go straight from one side to the other, right? And there's infinitely many more paths I can take, right? But a non-conservative force, for a non-conservative force, it matters what path you take. It doesn't just matter the displacement, the ultimate displacement, where you start and where you end. All these answers, your change in energy or the amount of work done, right, on that object by the force, will depend on which path you take. Okay, so a very, very classic example. So this is, so in non-conservative forces, so in non-conservative forces, path matters. You would say it's path dependent. Okay, so a classic example is, let's just say, friction, right? If the force that's acting on this guy, could be whatever it is, let's say it's like a hockey puck or something, right? Or a shoe, you're dragging a shoe, whatever. If you go straight from here to here, friction's only acting for that little bit, right? Okay? In that case, you're going to have one set of work, right? A smaller work, right? But if you instead drag that shoe along this, like, I don't know, let's say it's like a rough road or something like that. You drag this shoe along a rough road for this longer amount of time, for a farther path, right? Even though your displacement's the same, you're ultimately ending at the same spot, this longer path is going to have more work, right? It's going to take more work to do it because you're working against the frictional force over a longer distance. Okay? And if you take this even longer path, up here, up, over, around, and on, around, you are going to get even more work, right? It's going to take more work to drag this guy along, this shoe or whatever it is that you're dragging. It's going to take more work to drag them along this path, getting from A to B, even though you still begin and end at the same spot. Okay? So non-conservative forces, the path is very, very important. The path matters. The two biggest, the ones that we'll see in this class, are friction and drag. Okay? These guys are non-conservative forces. All right? But let's look at another type of force. Okay? And that force, as you can imagine, is called a conservative force. And these are neater. These guys, their bookkeeping is a little bit nicer, and they're easier to work with, although we can still work with friction and drag, which we'll see later. But these guys are nice. These guys are called the conservative forces. Okay? So we say conservative forces. And these guys are path independent. And what does that mean exactly? Well, it means that, let's take gravity, for example. Gravity is a very, very classic conservative force. Okay? And so let's say that I take an object and I want to move that object from here to here, right? So how much work is done? Well, the work done is equal to the change in kinetic energy, but the change in kinetic energy is equal to the change, negative the change in the potential energy. This is something we're going to be learning soon, but this is one consequence of conservation of energy, okay? And so that means that the difference in energy between here and here, or the work done, is simply equal to mgh, right? If this is h equals 0, and this is h equals, our whatever height we have, right? Then the work done will be mgh, okay? That's the amount of energy this guy gained from going from A all the way up to B, okay? Now, what if we take a different path? What if we go from here to here like we did last time? Well, again, if this h is still h, right, the work we did is the exact same, even though we took a different path, right? And what if we just did this crazy path? Is that enough? Okay. Again, the change in height is from 0 to h, so the work is still the same, mgh prime. For conservative forces like gravity, the path doesn't matter, right? It's not like friction where we're working against the friction the entire time, right? And then we get it there. It's not like that, right? It's like sometimes gravity's helping us, right? In this case, if we're going down, and then sometimes we're working against gravity, then gravity's helping us, working against gravity, and the net difference is just the change in height, okay? So it doesn't matter which path we go for gravity, work is equal to mass times gravity times height, okay? Another great example of a non-conservative force is the electromagnetic force. Or sorry, another example of a conservative force is the electromagnetic force, which we get into in the next semester, okay? Physics 131. But these are the two conservative forces that we'll be using the most, and these guys are the forces that we focus on whenever we're doing conservation of energy problems, okay? Most conservation of energy problems that we do will be in the world of gravity or in the world of electromagnetism, but it still turns out that we can solve a whole lot and make a lot of predictions about the future, even just using these two main forces. And when you think about it, those two are the two biggest forces that we see in our ordinary lives anyways, right? We don't see the weak nuclear force and the strong nuclear force so much in our day-to-day lives, okay? Why do I make this distinction? Because it turns out that when we're doing conservation of energy, we are almost always going to be focusing on conservative forces, not non-conservative forces, okay? So at least at the very beginning, we're focusing on conservative forces. Now, there's little tricks you can do to take into account friction and drag. And we're going to talk about that too. But for now, just know that when we're talking about solving conservation of energy problems, it'll almost always involve gravity or the electromagnetic force, okay? And in the next video, I will show you Scott's 5-step process for any conservation of energy problem. Okay, I'll see you there.